now it is time to derive one of the most important results in all of physics, okay? F equals ma is paramount in first semester physics, okay? We're going to use F equals ma essentially until the end of the semester. But this is one of the most powerful results in all of physics, and it starts with this equation right here. So we already know that work is equal to the integral of force dotted into displacement, all right? Very tiny, tiny displacements. And this equation is true in general. If you get a constant force, okay, then of course F just comes outside the integral, and dx is just the total displacement along the path, and you recover the F dot delta x that we had before. But in general, that's not always going to be the case. So this is a general equation. Now, recall that F equals ma. So if I integrate along a path, and this is integrated along a path, and F equals ma, right? Remember that A is equal to dv dt. So what I need to do is substitute dv dt in here, and I'm going to get from xi to xf m dv dt dx. But by the rules of multiplication and division, I can switch where I want my denominator to be with impunity because it doesn't change the value of the product. So I can slide my dt underneath my dx, and now I have dt dx, and this is nothing but velocity. So this is the instantaneous velocity at some given point along the path, and now what I'm going to have is velocity, and I'm going to integrate my velocity with respect to my dv now. So this turns into v dv. And because I'm integrating along a path, but now I'm integrating with respect to velocities instead of positions, I need to change these from my initial velocity to my final velocity. And if I assume my mass is constant, then my mass will come out of the integral, and I just have v dv, the integral of v dv. And the integral of v dv is 1/2 v squared. So the result of this, if I put it up here, my work is equal to 1/2 mv squared from vi to vf, right? So this is equivalent to 1/2 mvf squared minus 1/2 mvi quantity squared. And this is what my work is equal to, right? 1/2 mv squared minus 1/2 mvi squared, all right? Now, why is that important? This is important because we give this quantity a special name, 1/2 mv squared. We give that quantity a special name. That name is kinetic energy. Okay, we really haven't defined energy yet, but as we'll see, that's actually a really fuzzy term. And so we actually just define the different ways that energy can manifest itself, i.e. kinetic energy, potential energy, internal energy, so on and so forth. So kinetic energy, 1/2 mv squared. Kinetic energy is the energy an object possesses as it's moving. Okay, the energy of a moving object, in other words. Okay, so kinetic energy is the energy possessed by a moving object. Or, actually more appropriately, it's the energy possessed in the motion of the object because the object is moving. It can possess, a moving object can possess other types of energy as well, but it's the energy that arises from the motion. Okay, so it's the energy possessed by the motion of an object is maybe a better way of saying it. Okay, now we know that work is equal to the final kinetic energy minus the initial kinetic energy. Right? That's exactly what this equation says. The work is equal to the final kinetic energy minus the initial kinetic energy, but a final minus an initial quantity is just a delta. So the work that an object has performed upon it by an external force is going to be equal to the change in its kinetic energy. And this is sometimes called the work energy theorem, okay? The kinetic energy, the change in kinetic energy of an object is equal to the work that that object has performed on it by some outside force, okay? So that is the definition of kinetic energy. So as a specific example, okay, let's just look at a one-dimensional case here. And first things first, let's just look at an object being pulled by a string on a one-dimensional surface. Actually, I'll tell you what, let's not even say it's pulled. Let's just say that it's moving, right? So the surface is frictionless, you give it a shove, and it just has motion, okay? It's in uniform motion. And let's say the mass of the object is 1 kilogram, and let's say the velocity of the object is 2 meters per second. So you give this a bit of a shove and it's sliding across this frictionless floor. What's the kinetic energy of this object? Okay, so the kinetic energy of this object is equal to 1/2 mv squared, right? And I don't have to worry about initial and final velocities because the velocity of the object is not changing. Now, here's the key. If the velocity of the object is not changing, it has no acceleration. If it has no acceleration, it has no net force. If it has no net force, no work is being done on this object. Once an object is in motion and it's staying in that uniform motion, according to Newton's first law, an object in motion will stay in motion, then the net work on that object is 0, okay? So there's no change in kinetic energy here. It's just going to possess this value of kinetic energy, which is 1/2 m, which is 1 kilogram, times v squared, which is 2.0 meters per second. Okay, so this is going to become 2 squared is 4, 4 cut in half is 2, so this is going to become 2.0 kilograms times meters squared per second squared, and you can prove to yourself that this is indeed the units of joules, so this is 2.0 joules, right? If I take away the squared here and I write my meters as meters times meters, then I have kilograms times meters per second squared, which is my newtons, times this extra meter, which is newtons times meters. So these units do indeed give you joules, okay? So meters times velocity squared also gives you the units of joules. Now let's do a slightly more complicated situation where let's say that an object is experiencing a pushing force of, let's say it's being pushed, and the pushing force is 10 newtons, and the initial velocity of the object is at rest. So you just have a block sitting on a frictionless surface, and you start pushing on it with a force of 10 newtons, and after 5 meters, we want to know what the final velocity is. Now, we can already solve this problem using Newton's methods, because if we know the mass and we know the force, we can get the acceleration. If we get the acceleration and we know the displacement that we're moving the object, we can then use one of our kinematic equations and solve this problem. But we want to use energy methods. So let's say that we are moving it a displacement of 5 meters, and at that 5 meter mark, sometime down here, I calculate or I measure its final velocity, and I want to predict what that final velocity is going to be. Well, I can use the work energy theorem, right? So the work energy theorem says that 1/2 mvf squared minus 1/2 mvi squared is equal to the work. And because I know the force and I know my displacement, I can calculate the work, and I know what my initial velocity is. I'm given the mass, so I can calculate my final velocity. Vf is the only unknown variable here. Now, a couple of things that are going to make this nice and neat. First of all, my initial velocity is 0. So if your initial velocity is 0, then this term goes away. Initially, it has no kinetic energy. It's not moving, all right? So that term goes away. And if I solve this equation now for Vf, what I'm going to find is that Vf is equal to, multiply both sides by 2, so I'm going to get a 2w. Then I need to divide this side by m, so I'm divide this side by m. 2 times my work divided by my mass, and then I need to undo my square here, so this is going to be the square root of 2 times my work divided by my mass. And my work is just my force times my displacement, which is divided then by my mass. So if I want to know what the final speed of this object is going to be, now why is the object going to gain in speed? Again, because it has a net force applied to it, it will accelerate. So as it's moving, it's going to get faster and faster and faster. This is just another way to find what that acceleration is going to be. So if I now plug in my numbers, this is going to be 10 newtons times 5 meters right? And what is this going to give me? My mass is 1 kilogram, and so 50 times 2 is 100. 100 divided by 1 is 100. Square root of 100 is 10. So my final speed here is going to be 10 meters per second. And we can also then convince ourselves that our units work out, because newtons is kilograms times meters per second squared. And my kilograms here are going to cancel with my kilograms there. And I'm going to get meters times meters, which is meters squared, over seconds squared. So I have meters squared over seconds squared, and when I square root that, I get units of meters per second. So that is how you can use the kinetic energy of an object to calculate certain things. You can either go from the work to the kinetic energy, or from the kinetic energy to the work. All right? So I hope that example was enlightening. In the next video, we'll talk about power.